Hi, and welcome to Allen High School's discussion of chemistry at the APIB HL1 level, talking about ionic bonding. In particular, we're studying lattice energy, and we're estimating lattice energy using this formula that the lattice energy is the charge of the positive times the charge of the negative over R, the distance between the ions. Now, if we want the highest lattice energy, and I just made up a silly question just to try to make it interesting. What we want to have the highest energy is we want the smallest R value, right? Because as we decrease R, we increase lattice energy. And we want the largest Q, because as we increase Q, we increase lattice energy. Let's start with our lattice energy reactions. A lattice energy reaction is the reaction of the gaseous ions. Very, very important. When we study energies involved in reactions, the state of the substances is a very important consideration. A reaction from aqueous ions is very different than a reaction from the gaseous ions, and we make the solid. You need to know that. You need to know the equation for lattice energy and include the states in that discussion. And then we have sodium ion. Again, it's got to be gaseous, plus chloride ion, gaseous, makes NaCl solid. Now, let's take a look at our conversation of lattice energy here. If you look at the periodic table, and remember when we long time ago, like a couple of days ago, we did the proton to electron ratio, and if you increase the proton electron ratio, you decrease the size. And magnesium and sodium, this is for isoelectronic substances, which magnesium and sodium are, we will actually see that the radius of magnesium is less than the radius of the sodium ion. I think it's pretty obvious that Q for magnesium, since it's 2+, is greater than Q for the sodium ion. We don't have to worry about the anion because we kept that the same in this example. So in both situations, both based on radius and charge, magnesium chloride is our clear winner. Okay, would provide the greatest amount of energy if those formed, if we could capture the energy, remember, released from the formation. When you form, you free. When you form, you free. All right, lithium chloride. So we'd have lithium, and I think I'm going to stop writing these in just a minute. Lithium gas plus fluoride gas makes lithium fluoride solid. Again, you should be able to recognize and write. Okay, we have the same ion, lithium gas plus chloride ion, gaseous, makes lithium chloride solid. Now, in this case, all of the charges are the same, +1 and -1. So the race comes down to radius. And since fluoride, the outer electron ends in N equals 2, it's smaller than chloride, which is N equals 3, so the fluoride wins. This would be lithium fluoride. Now, I'm going to assume based on this that you are okay with writing these lattice energy equations, and let's just do our comparison. Our radius of strontium ion is larger than our radius of sodium ion. We don't have to worry about isoelectronic or anything like that. Sodium's in the 3rd period, strontium's in the 5th period. So there's a pretty clear size differential there. But the charge of strontium is greater than the charge of the sodium ion. So if we look at our winners here, based on radius, you would think it would be the sodium ion. Remember, we want the smallest radius. But based on charge, it would be the strontium. But remember what I mentioned in that last slide. Charge trumps radius. And the radius differentials are going to be on the order of picometers. This is double. Okay, so we'd have to look them up to be exact, but we're making predictions, remember. So if I were to predict, I would say that the lattice energy for strontium chloride is greater than the lattice energy for sodium chloride because of that strong attraction between the +2 and the -1s. Now, there's another way to measure lattice energy, and that's the Born-Haber cycle. And if you are an IB, I want you to pay particular attention to this. We can get at the lattice energy in an indirect way. Now, we haven't had thermochemistry. I teach that all together with thermodynamics, but you certainly have had many discussions of the enthalpy of a reaction. Remember, if it's positive, it's endo, requiring energy. If it's negative, it's exo, releasing energy. What is nice is that because of the type of function this is, we can get at it in a variety of ways. All that matters is where did we start and where do we end. It doesn't matter how I get from start to end. I can go directly start to end that way, or I can go start to end all the way like this. With this kind of function, it doesn't matter. The only thing that matters is the starting point and the ending point. And so what we do is calculate the lattice energy by coupling or combining. This coupling of energy is a very important concept of a variety of processes. Now, again, we haven't had thermodynamics, but I think we'll be okay with this concept of enthalpy. So what we're after is our lattice energy. So do you remember our lattice energy was getting the solid, like I'm just going to make it up, lithium chloride solid, but it was from the gaseous elements. So the gaseous ion up here and this gaseous ion. And so what we can do is add up the different energy values. So first thing we're going to do is take the metal, solid, and make it a gas. All right? So if we take solid and make it a gas, that's a sublimation. Okay? And we're going to do that to the ion as well, to the cation. So we're going to take the nonmetal and we're going to make a gaseous nonmetal, and that's sublimation energy. Then what we're going to do to the metal is we're going to form a gaseous positive ion. That, remember, if we take an element and remove an electron to make a positive ion, is the ionization energy. Okay, as long as it's gaseous, we got to be in the gaseous phase for that as well. That's another energy you should know, by the way. All right. Now, this time you notice that going from the gaseous nonmetal down to the gaseous ion is exothermic. Remember our electron affinity? Tends to be negative or favorable. Okay. So if we add these up and add up all these energies, and one we haven't talked about yet, where we take the two elements and go to the compound, that's called a formation. A formation is the energy in going from the elements in their natural state, which for a metal is going to be a solid, to the compound. Okay. Then if we add all those up, we're going to get our lattice energy. This is what we wanted right here, is the lattice energy. And that's kind of complicated, but that's the Born-Haber cycle. This shows an example of one with sodium chloride that hopefully you can get at pretty clearly. If we take sodium and half of a diatomic. Again, I know those don't really exist, but they do mathematically, and we're dealing with the mathematics of energy. So if you took sodium plus chloride, you would make 1 mole of sodium chloride. That is the definition of formation from elements in their natural state, which is for sodium, for chlorine, it's gas, making the compound. All right? So that's one energy piece that we need. Now, if we take sodium solid and go to sodium gas, this is called the atomization, but it's basically the sublimation of that. And then from here to here, we took sodium gas and made sodium ion. Okay? From here to here, notice what we did from here to here. We basically broke that bond. Instead of having Cl2, we have Cl. All right? And then here we added an electron to the Cl. So we formed that. And then finally, if we add all those up, if we combine all those processes, we would calculate the lattice energy. All right? So that's the Born-Haber cycle. And especially for your IB kiddos, I needed to introduce that to you. All right, we are going to forge ahead into our next topic, which is covalent bonding. And we're going to do some modeling, and I hope have a good time with that in class. So until then, this is signing off.